Gradient descent isn't just useful for regression problems that predict continuous values, it's also essential for classification problems like determining whether an email is spam or not, predicting whether a customer will buy a product, or diagnosing diseases based on patient data. One of the most common classification models is logistic regression, and just like linear regression, it relies on gradient descent to find the best model parameters. Unlike linear regression, which predicts numerical values, logistic regression predicts probabilities. Instead of modeling a straight line, it models an S-shaped curve using the sigmoid function, which transforms any input into a probability between 0 and 1. The formula for the sigmoid function is sigmoid of z equals 1 divided by 1 plus e to the power of negative z, where z is the weighted sum of inputs, just like in linear regression. The sigmoid function ensures that outputs are always between 0 and 1, making it ideal for classification tasks. If the output is greater than 0.5, we classify the result as one class. If it's below 0.5, we classify it as the other. Just like in linear regression, the goal of logistic regression is to find the optimal values for theta, the model's parameters. But because logistic regression deals with probabilities instead of direct numerical predictions, we can't use the mean squared error, MSE, cost function like we did before. Instead, we use a different cost function called the log loss function, also known as the binary cross-entropy loss. The formula for log loss is cost function equals negative 1 divided by m times the sum of actual value times log of predicted value plus 1 minus actual value times log of 1 minus predicted value. This cost function penalizes incorrect predictions more heavily when the model is very confident but wrong. If the actual label is 1 but the predicted probability is close to 0, the loss is very high. If the actual label is 0 but the predicted probability is close to 1, the loss is also high. This makes the model adjust its parameters carefully to reduce mistakes. To minimize this cost function, we use gradient descent, just like in linear regression. The update rule for logistic regression is almost identical. New theta equals old theta minus learning rate times the derivative of the cost function with respect to theta. Since the sigmoid function is differentiable, we can compute the gradient and iteratively update the model parameters until convergence. The learning rate still plays a crucial role. Too high and the model jumps around. Too low and training takes forever. One advantage of using logistic regression with gradient descent is that it scales well for large datasets. Unlike normal equation methods, which compute the exact solution, gradient descent allows us to optimize logistic regression efficiently even when we have thousands or millions of features. This makes it a powerful choice for real-world applications, including fraud detection, medical diagnosis, and customer churn prediction. However, logistic regression is just the starting point for more advanced classification models. In deep learning, for example, we don't just have a single layer of weights like in logistic regression. We have multiple layers of neurons, all trained using gradient descent. The optimization principles remain the same, but the computations become much more complex. This brings us to one of the most important applications of gradient descent, training neural networks. Logistic regression is a simple example, but deep learning models take it to another level, requiring backpropagation, weight updates, and massive datasets to achieve high accuracy. So how does gradient descent work when training deep neural networks? Let's explore how it powers some of the most cutting-edge AI models in the world. Gradient descent is the backbone of modern deep learning. While it works well for simpler models like linear and logistic regression, its true power is unleashed when training neural networks. These are the models behind image recognition, natural language processing, and even self-driving cars. Unlike traditional regression models, Neural networks consist of multiple layers of interconnected neurons, each with its own set of parameters that need to be optimized. This makes training them much more complex, but the fundamental principle remains the same. Use gradient descent to minimize the error and improve predictions over time. Training a neural network with gradient descent follows a specific process known as backpropagation. This is how deep learning models adjust their weights to learn patterns in data.